Good morning, everyone. This is Roland Demko with Acromag, and I have with me here Erica, and she's our engineer on our 10 gigabit Ethernet solution, and we're going to talk to you about applying 10 gigabit Ethernet interface solutions for embedded computing applications today. So without further ado, we're going to move into the presentation here. As I mentioned a moment ago, and the title is here so that you can see 10 gigabit Ethernet interface solutions for embedded computing applications. Today's discussion is going to have a number of different parts to it, and we're going to be talking about why 10 gigabit Ethernet communications is important, why is Ethernet, specifically for 10 gigabit Ethernet communications, important. We'll talk a little bit about the media for 10 gigabit Ethernet, the standardized open systems interconnect, which many of you should be familiar with. It's called OSI. The implementation resource requirements to drive an Ethernet port, and more specifically a 10 gigabit Ethernet link. Implementation strategies for the TCP IP stack. We'll talk about Acromag's new XMC-6280, which Erica here is going to elaborate on, since she's the chief engineer on that project. And we'll talk about performance, 10 gigabit Ethernet versus some of the other networks and the like. We'll talk about the 6280 architecture, a little overview on the hardware, on the software. We'll talk about applications where 10 gigabit Ethernet excel, and pricing availability, and then we'll try to answer any questions that you may have at the conclusion of this presentation. To start, why is 10 gigabit Ethernet communications important? Well, today people are tending to generate more and more information, and when you generate more and more information, you need to be able to store and move a lot of that information. So that's why moving large amounts of information quickly and easily over large distances is very, very important. You need to be able to connect all of your fast data generators to the analysis tools and to the storage engines that might be waiting for that information. You want to follow standards for protocol, for software and for hardware. This would make the transmission of that information something that people already have an infrastructure already in place to accommodate. And you also want to have hardware and software that are available today at a very reasonable price. And I guess if that hardware and software is available today, the big question is if you're not moving large amounts of information, what are you waiting for? Why is Ethernet for 10 gigabit Ethernet communications important? Well, Ethernet is a proven worldwide standard. Any place you go in this world today, people are using Ethernet. You're probably using it at your desktop as we speak today. The software integration cost is the same as that for other Ethernet networking, and a lot of the experience and the knowledge base that you've already acquired from installing and getting your Ethernet communications in your office and between other peripherals in your facility or in your application, it's all reusable. The media, as probably many of you are available, as many of you are aware, is either fiber or copper, RJ45, more commonly known as Cat-X, and there's a number of different designations there, but both fiber and copper are available. And just to review a little bit for you what the standardized open systems interconnect, the OSI TCP IP stack is, we're going to go through some of the layers here. Just so you remember and refresh your memory. First, there's the physical layer, and this is where you'll find either your copper or your fiber media. Above that, you'll have something called the data link or the MAC layer. This is where packets of information are transmitted between node to another node. Okay, and this is all done with a station address. Now, if networking should be involved, in other words, moving from one network to another network, there's a network layer that actually handles the routing information in the address fields to move information between one network and one or more networks. There's the transport layer that sits on top of that, and that ensures that there's actually an entire message or file delivered from the source to the destination. The session layer basically starts and stops the flow of information. The presentation layer ensures that right above that is the applications layer, but it ensures that the information that's received at a particular node is then transformed into the appropriate information types that the application layer can use. And then there's the application layer. This is the layer where you may have an email, or you may have a particular set of cryptography or something going on with your information, analysis of the information, but basically at that point you want to have information that you can read and understand, which is the job of the presentation layer, and you can do your job. And then when you go ahead and make a retransmission through this whole model again, if you were going to send that information to another node, it would be going through the same model in reverse, from the application layer back through the presentation layer, back through the session layer, and on. If you look at the implementation resource requirements for this model, you're going to find that the heaviest portion of that model is from layers 3 through 6. And you'll see that CPU usage is the max, and memory usage can be very, very large as well. So CPU, memory, and bus speed, all of those things impact how fast information moves from the physical layer up through and to the application layer. Knowing this, that there's a hardware interface that needs to be driven, and that there's a resource-intensive software protocol to be executed, what are some of the popular scenarios that people use today to basically implement this stack? Well, one of the simplest is to use the CPU to drive the OSI stack. And sometimes to gain increased performance, what they might do is they might use something called the OSI Enhanced Performance Architecture. We'll show you what that is in another minute. And then the best is to use either a silicon or an ASIC-based hardware assist stack, which basically is a hardware TCP offload engine, more commonly known as a TOE. If we look at CPU execution of the TCP IP stack, the first and probably the simplest implementation is when you have a single core CPU, which many of us had in the past, you reserve a block of that single core CPU, both memory and compute power, and that's used to drive the TCP IP stack. Now, if you look at what computers have become, today we have a lot of multi-core CPUs, where you may have, for instance, a 4-core or even an 8 or a 12-core CPU. But let's look at a 4-core CPU, and let's dedicate one core, perhaps core 3, to driving the TCP IP stack. Now, all of the unused space here, the memory and the compute power, and here, is available for your application. But the TCP IP stack, if we dedicate a whole core to it, basically that's going to be dedicated to doing communications. And your applications area is generating information or processing information coming from or being sent out through these TCP IP stack drivers and resource requirements here. And that's where you're actually doing your work. This is solely for the purpose of moving the information from one node to another. So what can you do to make that execution of the communications interface faster? Well, the first is just go to a faster CPU. I mean, you know, you've got 1 gigahertz, 2 gigahertz, 3 gigahertz CPUs. So the faster the CPU is, the faster you can execute that communications, and also the faster you can do the applications work. Another way is to use something called the OSI Enhanced Performance Architecture. Now, if you look at that, what it did was it streamlined layers 3 through 6 and basically collapsed those and made a direct connection between the application layer and the data MAC layer, the data link layer. So all of this logic is basically eliminated, and what that means is that you have knowledge of the application when you first wrote it, and you know that none of these other layers are actually going to be involved with making the information usable when it gets to the application layer. So basically you're sending information in a ready-to-use format to this node so that it can be used by the application layer. And this definitely does reduce the overhead for driving the TCP IP stack. All of this comes at a cost, and the cost is that you do lose the flexibility that is standardly presented in layers 3 through 6. So what can you do to basically preserve all of the flexibility of a fully implemented OSI stack and not have to sacrifice in any areas such as this? Well, this is the reason that Acromag came up with, and we developed something called the XMC-6280. It's an ASIC, a silicon stack on an XMC module. And no standard capabilities need to be compromised. You have a lot of additional capabilities that you would even have to write code for if you were to do this in software. For instance, we have IPv4 and IPv6 switching and routing. You can support 1 gigabit and 10 gigabit. And the transmission protocols, well, the transmission protocols are TCP, UDP, iSCSI, and fiber channel over Ethernet. At this time, I'd like to turn this over to Erica. Erica is the engineer on our project here, and she did a lot of work in making this card a reality and making it something that I think you're all going to find benefit of. So Erica, I'd like to turn this over to you. Are you ready?
Yes.
Okay. All right, here we go.
So before we go on, I'll explain a little bit about these transmission protocols that we support. There is TCP and UDP, which are the most commonly used for network attached storage, and that's file oriented. TCP you will see the most often, and most of you guys are probably familiar with. The UDP, however, is a lot of the time you'll see it used for streaming video. And then we also have the iSCSI and FCOE, fiber channel over Ethernet. And that's for block level storage, or what we would call SAN storage area networks. And usually we would connect to these using fiber channel technology. So instead of using the fiber channel, it's a whole lot cheaper and faster and easier to manage an Ethernet connection. So these two protocols right here will allow you to use Ethernet instead of your fiber channel. This is really great because you could use one card to communicate to both the network attached storage and the storage area networks, which usually you can't do that. Here we have a performance comparison of the software stack and the silicon stack. The throughput per port sustained in megabytes per second is 425 megabytes per second for the 1 gigabit Ethernet silicon stack. It's 2,500 megabytes per second full duplex for the silicon stack, the 10 gigabit Ethernet. And then for the software stack, you are limited, no matter what, to 40 megabytes per second. And this is a big deal because even though you have those 10 gigabit Ethernet connections, you are limited to the 40 megabytes no matter what. So even if you dedicate a single core to the whole software stack, you're still going to get 40 megabytes per second. And then we'll move on to host overhead, which is very low for the silicon stacks and very high for the software stacks because the software stack is located inside your CPU. Then we have your latency, 15 microseconds for the 1 gigabit silicon stack and 10 microseconds for your 10 gigabit silicon stack. That is 250 microseconds for both of your software stacks. And then we have determinism, which is your variation in your latency. We have plus or minus 2 microseconds for the 1 gigabit and 10 gigabit Ethernet silicon stacks, and plus or minus 200 microseconds for the 1 gigabit Ethernet and 10 gigabit software stacks. Then we have the reliability under load, which is also a big deal. For the silicon software stacks, under any load, heavy or light, the load is taken out of the equation. It works excellent under both types of loads. And then for your software stacks, it's always going to be poor under a heavy load. Here I'm going to go over a little bit of the XMC-6280 architecture. We have P15 over here, which is our XMC connector. It has 8 lanes of PCIe Gen 2, and that's 5 gigabits per lane. So we do get 40 gigabits, but with your 8B, 10B encoding, you're going to get around 32 gigabits of data. And typically you'll see around 27 gigabits of data going through this P15. So just keep in mind that you will be limited if you're using all 4 ports, that you will be limited to around 27 or 28 gigabits per second there. But okay, that's our P15 interface. And then we have our serial EEPROM. This is where we store our configuration data for the all of the PCIe information and the ASIC as well. Then we have our serial flash. This is where the ASIC firmware is stored. Our reset, it runs off of a 50 megahertz crystal. And then we have our DC to DC converters, which these convert 3.3 volts and 5 or 12 volts from P15 to 1 volt, 1.2 volts, 1.5 volts, 2.5 volts, and 3.3 volts, which are all used by this ASIC. We have our DDR3 up here, which holds buffers and connection information for all of the offloading. This will allow for up to 32K offloaded connections right here. And then we have our 4 SFP plus ports. Keep in mind that you will be able to use the SFP modules as well. And then we have an I2C right here. This is the ASIC. A little bit more about the hardware overview. This is a single wide XMC module using a maximum of 8 PCIe lanes at Gen 2 speeds. You can also use PCIe Gen 1, but keep in mind that it will be severely restricted in the speed. You can also use a 4-lane PCIe connection, but again, you're going to be restricted. And 16 lanes will be fine, but it will only use the 8 PCIe lanes at Gen 2 speeds. Then we have our 4 SFP or SFP plus ports for either copper or fiber connections. SFP is for 1 gigabit Ethernet, and then SFP plus for 10 gigabit Ethernet. We support up to 1 million connections, and 32,000 of those can be offloaded. Our latency is 2 microseconds end to end. Determinism, plus or minus 1 microsecond. Throughput, 2,500 megabytes per second, as I said before, and it's per port at 10 gigabit Ethernet full duplex. As I showed before, we have 5 gigabits of DDR3 memory for most of the offloading information. And then we have our options and accessories that are available. We will have a passive copper 1 meter patch cable available, and then SFP modules for copper and fiber. Those are the 1 gigabit modules. And then I'm sorry we don't have them in here, but we also have SFP plus modules coming, and those will be in copper and fiber as well. There are short reach and long reach available. And then a little bit of our software overview. Our supported operating systems are Windows 7 and Linux, and I'd like to make it known that Linux is 64-bit. Windows 7 we can do 32-bit or 64-bit. We support 1 million connections. There is complete and flexible TCP offload per connection, so you can have one connection that's offloaded and another that's not. Then we have zero copy direct data placement, which is otherwise known as IWARP, Internet Wide Area RDMA protocol. And this is for remote direct memory access. So you can actually DMA from the memory of one computer to the memory of another computer without involving the operating system of either computer. And then we have traffic filtering and management, which Roland will talk about a little bit more later. And then packet switching and routing. So you can go from any import any input port to any output port, wire to wire, or any output port to any input port, which is host to host. And then I will let Roland talk a little bit more about the applications of the card.
Okay, now we've got all of that technical detail stuff. And what we're going to do is talk a little bit about some of the applications where 10 gigabit Ethernet makes its presence very, very well known. And we talked about a little bit of this earlier, but I listed a couple of things below there, and any one or any combination of these key application characteristics would dictate using the 10 gigabit Ethernet cards, such as the XMC-6280, moving lots of data very quickly. PCIe systems requiring media flexibility, copper, fiber, a combination of them. Now, we also have another module coming out, and it's the XMC-6280, which is actually going to not use the copper and fiber off the front, but actually be using the backplane for communications of the information. And then there's also converting and being able to deal with systems that are a hybrid of IPv4 and IPv6 systems. Offloading communications, as we talked about. We'll talk a little bit about traffic filtering and management. The rugged form factor for this card, we've got some extreme memory specs and shock and vibration and the like. And basically, we intend it to be used in deployed systems as well as other systems. And then there's some packet switching and routing, any input port to output port, and any output port to any input port, wire-to-wire, host-to-host communications. Well, the first one is moving lots of information very, very quickly. Now, you got to understand that 10 gigabit Ethernet is full duplex. Okay, so we were talking earlier about 2,500 megabytes per second. Yes, that is true, but it's 1,250 megabytes in one direction and another 1,250 megabytes throughput in the other direction. So combined, you really got 2,500 megabytes per second, but this is the full duplex throughput. So you've got 10 gigabit Ethernet being able to move a lot of information very, very quickly. There's flexibility in the medium. And here you see our single card has 4 SFP or SFP plus ports on it. You could have a 10 gigabit fiber. You could have a 10 gigabit Ethernet on copper. You could have a 1 gigabit on copper. You could have another 10 gigabit on fiber. You can mix and match. And this card gives you the ability to route in between the different SFP, SFP plus ports, and also to connect to different devices that may be using other standards, wire or copper, SFP type, 1 gigabit or 10 gigabit Ethernet communications. You also have the ability to add IPv6 to older systems. Way back, it was all IPv4 systems, but today so many of the new applications are now using IPv6 so that they have a lot more IP addresses available. This card will permit routing between IPv4 and IPv6 networks through configuration, and this makes it very, very advantageous if you were to take an older system and incorporate this card. You can talk to IPv6 devices and bring them in and convert them into a more local IPv4 address for your internal consumption in that older system, perhaps. We talked about offloading the communication software earlier, and basically what you had was, if in a single core computer, this was the amount of resource, being memory and performance, that was being eaten up with the communications activity. And in a multi-core CPU, we actually took up maybe one whole core. If we put the new XMC-6280 in there, you're only going to take a small smidgen, basically, on both sides and free up the rest of those cores for use for applications work. Basically, all you need to do is basically configure and let the card do its job. Now, traffic filtering and management, this is something where you try to define a quality of service for end-to-end transmission. And one of the things that happens with Ethernet is, because Ethernet can be used for higher priority and lower priority traffic. When you have lower priority traffic, it can hog a standard Ethernet communications link. And I'm sure many of you have used 1 gigabit or even some of the slower varieties of Ethernet, and someone did an FTP transfer of multi-gigabytes, and all of a sudden the whole network performance went down. Well, on this card you actually have the ability to flag certain node addresses and say that packets coming from or going to a particular node address have higher priority than others, and the lower priority information would actually just be let to wait a little while. And that's a great thing, because Ethernet is used more and more, not only for just data communications, but also for control. And control applications require that you have a certain overall time period within which you want to get an answer, a little more of a deterministic requirement. So using some of the features on this card, you have the ability to configure certain ports to make sure that higher priority communications are actually recognized as higher priority communications, and you can actually perform some level of control over Ethernet. We built this card to be rugged, and you'll notice on this card here that this is the bare bone card, but we've actually put a heat spreader on here, and it's set up for partially for conduction cooling, but this is actually going to be used more so when we get to the Zowie card. But it is rated for a very, very extensive temperature spec, and we also have, as I mentioned, the conduction cooled version called the XMC-6280. I think the CC is still on the end of that. Is that correct? Yeah, typically we use CC for conduction cooling. But since the 6260 only comes in conduction cooling, I was just wondering whether we were going to attach the CC to it, but we did. Good. So it's consistent at least, so you can remember that. And I can remember it as well. These cards are compatible with VPX. They're compatible with other PCIe chassis architectures. If you're using a standard PCIe chassis, you would have to use probably a carrier card, and we have carrier cards that would accommodate this and let you use it into a normal server class machine or a desktop machine if you had that kind of data to move around. But we do have the conduction cooled version, which would be for use directly in a lot of the VPX systems that you'll see coming and the like. So this card was designed basically to satisfy the military, and as a subset of that, it will satisfy any office environment or more stringent laboratory environment. Packet switching and routing. Well, this card is unique in that it has 4 ports, and you can switch between the ports on the card. And it has the ability basically to route information between one port and another, and to basically permit bridging between one network and another. So this card is very, very powerful. It does not sacrifice any of the features that you find in the OSI stack. We were talking about using the OSI enhanced architecture where you eliminated part of the software. This lets you use the full advantage of the OSI architecture and switch between whatever networks are coming into and through the XMC-6280 card. Now the interesting part, the list price, $27.50. Of course, quantity discounts do apply. It's only available from Acromag. There is no one else who has an XMC module in this category and with this level of performance and 4 ports on it. We're taking orders now, and delivery is basically a little closer to the 3 weeks right now because we've had some overwhelming demand, but it will be stocked to 3 weeks in the near future once we get production up to speed. And with that, we hope that you're going to find some nice applications for this card. We try to outline where it fits. And if you should have any questions, and we're going to open this panel up for some questions right now, both I and Erica are here, and we will welcome talking with you and seeing if we can be of some assistance in helping to answer some of the questions you might have.
No questions right now, Roland.
Okay. If there are no questions right now, this is being recorded, so it can be played back at any time in the future. Is that correct there, Karen?
Yes.
Okay, so we'd like to thank you for your participation today, and we hope that you'll find a 10 gigabit Ethernet solution in your near-term future. Take care and have a very, very wonderful day. Bye-bye now.